All right, so welcome to the second video from chapter 5, still in section 5.1. And we're trying to, in this video, make sure we understand this key observation. Okay, so why don't you pause, copy, and then I'll chun it. All right, so the key observation for bootstrapping that we need to understand through this video is that for most statistics like mean, median, trimmed mean, most of the test statistics we might want to look at, the bootstrap distribution approximates the spread, bias, which we'll define later, and shape of the actual sampling distribution really well. But the center of the bootstrap distribution tends to be at the center of this initial sample, not at the center of the population. Okay, so conclusion is bootstrapping is really good for approximating the actual sampling distribution other than the center. So we wouldn't use the center of the bootstrap distribution by itself. Okay, so this panel works through section example 5.1 from the text. So why don't you copy it down, and then I'll start chunning on. All right, so in example 5.1 and 5.2, we're going to tell you the population that the data is coming from, which is not realistic, right? But we want to compare how the bootstrap does with the population and the population sampling distribution. So in example 5.1, our population is coming from a normal distribution with a mean of 23 and a standard deviation of 7. And we wish our test statistic to be a sample mean, where we're trying to approximate this mean of 23, like if we didn't happen to know it. All right, well, so process one, we're going to calculate the sampling distribution, the actual sampling distribution, not using bootstrapping, but the actual sampling distribution since we know the population. So how that goes is I'm going to take samples from the population, and I'm just going to arbitrarily pick the samples to have size 50. So grab 50 values in this normal distribution, compute their mean, record it, create the histogram, and then with that histogram, we could calculate our X bar and say that X bar approximates the mean of the entire population, okay? Now I could do that via R, but since this thing's normal and we've had Math 313 and we love the central limit theorem, we could actually compute X bar's sampling distribution theoretically, okay? And we've done this in the past, right? The mean of X bar will be 23, and that's where I do the expected value of X1 plus up to X50 over 50. I drag the 50 out, I distribute the expected value across X1 through X50, and I do the same thing with the variance. And so I get a standard error of this actual sampling distribution to be 0.99, okay? Or if I didn't know the population, let's just say I was given a sample of size 50 from the population. We got one sample of size 50. I calculate the mean of that sample, and it happens to be 24.13. We'll just observe slightly larger than the population it came from. But if you just give 50 values, your mean might be a little higher or a little lower than the actual mean of the population. I'm going to now bootstrap it. So I'm going to take 10 to the 4th resamples of size 50 with replacement. Each time I do so, I'm going to compute and record that X sub I, and then I'm going to create my bootstrap distribution from it, or R is, right? And it's going to tell me what the average of that bootstrap distribution and the standard error of that bootstrap distribution. And I get that the average, the mean is 24.15 and the standard error is 0.92, okay? All right, so here's a table sort of summarizing all this information. I have my original population, whose mean was 23 and standard deviation was 7. I had the sampling distribution, which I calculated theoretically, and its mean was 23, and its standard deviation was 7 over root 50, which is 0.99. And we did that with 313 knowledge. I was given a sample. It happened to have a mean of 24.13, and it happened to have a standard deviation of 6.69. You know, I didn't tell you that, but it did, let's just say. I then bootstrapped the heck out of that initial sample 10 to the 4th times and looked at the bootstrap distribution, and its mean happened to be 24.15, and its standard deviation happened to be 0.92. So here's the take home. The bootstrap distribution standard deviation and the actual sampling distribution standard deviation are close. The means are not. But the bootstrap distribution mean and the bootstrap initial sample mean are pretty close, okay? So there appears to be a nice link between these two values and these two values, okay? In your book, I'm going to hold this thing up. I don't know how this will work. So on page 108, figure 5.2, there is the normal population. There is the actual sampling distribution of X bar when I take samples of size 50. Here is, I think C is here's my sample, just how it played out. And then here's my bootstrap distribution based on that sample. And what you should note is that the shape of the bootstrap distribution and the actual sampling distribution look pretty similar. Similar spread, similar shape, but their centers are a little bit off from each other. Okay, so let's do another example like this from the book. And that is, whoops-a-daisy this way. That is example 5.2. Okay, good. So pause, copy, play. All right, I'll be doing a little bit of R here. So here again, we're going to have the same setup as before. I'm going to tell you the population, right? So the population here happens to be a gamma distribution with R equals 1 and lambda equals 1/2. So from 313, we know the mean is 2 and the variance is 4. And I'm going to calculate the actual sampling distribution. And I have to specify the sample size, so I'm just going to say 16, okay? So here, if I was using R would grab samples of size 16 from this population and it would record the sample mean, and it would do this 10 to the 4th or 10 to the 5th times, create a sampling distribution, and then do the mean and standard error, okay? We could also do this theoretically since gamma is a friendly distribution. It turns out that the test statistic X bar is also gamma distributed with parameters n times R and n times lambda. So the mean of the sampling distribution would be nr over n lambda, which is 2, and the standard error would be the square root of its variance. Variance would be nr over n lambda quantity squared, which turns out to be 0.5. Okay? Or I could do bootstrap. So I'm going to take a single sample of size 16 from the population. And when I did this, I had R do it. It gave me a mean of 2.74 for that sample and a standard deviation of 2.61, sample standard deviation of 2.61. From this single sample, I'm going to resample 10 to the 4th times with replacement. Each time I'm going to calculate X bar from that resample, create my bootstrap distribution, and then have R create the bootstrap standard error. And then I create a similar table, okay? Population, I knew the mean was 2, the variance is 4, so the standard deviation is 2. Sampling distribution, we computed that theoretically. Sample was given to us, we had R compute some things, and then we had R do the bootstrap distribution. And again, note the bootstrap distribution and the sample seem to pretty much agree with each other on their means. And the bootstrap distribution standard deviation seems to be close to the actual standard deviation of the sampling distribution. All right, well, let's just go to R to figure out how it did this bootstrap stuff. Okay, so this is line 31 in the chapter 5, our folder from Canvas, looking at example 5.2. And in line 33, I'm going to start by taking a random R gamma, or random sample from gamma distribution. 16 is how many values I'm sampling. And then I've got my R equals 1, my lambda equals 1/2. And I'm going to calculate the mean of that sample. So grab sample, calculate the mean. And now note, this sample has a different mean than the one I had on the board, the one that you'll have on your R simulation. Okay. All right. Well, now I'm going to run a bootstrap on that one sample called my.sample. I'm going to run it 10 to the full times. I'm going to create a vector called my.boot to record the sample mean of all these 10 to the fifth samples I'm doing. All right, and then for each from 1 to capital N, I'm going to define X, and it's going to be a new sample. So I'm going to take my sample. I'm going to grab 16 of these values from my sample, allow in the replacement. That's going to be X. And then I'm going to calculate on line 41 the mean of X and record it in that vector of my boot. So let me highlight lines 36 to 42 and run them. And a few notes still running. There we go, we're done. I can crank out a histogram of that thing. And there it is. The mean of my boot is 2.2882, which by the way is pretty close to the mean of the sample of 2.2872. And the standard deviation of this bootstrap distribution is basically 0.6. Okay, so slightly different than my values, but hey, we can do it. Right. So let me stop sharing that. And again, in the book on page 109, they give some figures. So here, all right, there is the graph of the gamma distribution and its mean in the dotted line. Right here is the actual sampling distribution of the mean of 16 values randomly chosen. Down here is an actual sample of size 16 selected from the gamma distribution. And then over here is the bootstrap distribution of X bar based on that sample. And again, I'm hoping you note that the two sampling distributions, the actual versus the bootstrap, look a lot alike, though they are not centered in the same spot. All right, so what are the take-homes from this? Take home number one, those figures I just showed you. The bootstrap distribution looks pretty much like the actual sampling distribution, but it's centered on the mean of the sample, not the mean of the population. The actual sampling distribution is centered on the mean of the actual population. The bootstrap distribution is centered on the mean of the bootstrap initial sample that we bootstrapped off of. So that's one observation. So take home two. Bootstrap distribution, it's a pretty good estimator of the sampling distribution apart from the center, okay? But spread and shape, it seems to do a pretty good job. We'll oftentimes compare the center of the bootstrap distribution with our observed statistic from the original sample that we bootstrapped, because if they differ, it indicates that there's some kind of bias going on in our bootstrapping model. So here, the difference is 0.01, virtually zero. So it doesn't look like the bootstrap model has any bias compared to that sample it was bootstrapped off of. And we'll talk more about bias in videos to come.